Hello, this is my oral presentation for the internship before cohort. Yes, on embedded systems. So the topics covered were introduction to embedded systems and microcontroller, C programming, PiximLab, which was a simulator used to simulate the functions and the workings of the PIC 16F877A, microcontroller architecture that involves the datasheets, programming the microcontroller, peripheral interfacing, communication protocols, and the black box project. So, an embedded system is a specialized computing system with chip-enabled hardware and software to perform a specific task or application. It has some benefits, which are lower power consumption, low cost, high performance, and its applications are everywhere. For example, in cars, in washing machines, and microwaves. So there are many types of embedded systems. We have simple ones, complex ones, standalone real-time networks, mobile and hybrid embedded systems. So examples of simple embedded systems are digital clocks, temperature monitors, and smart fridges, while those of complex embedded systems are missiles, routers, Alexa, yes. So the major components of an embedded system are either a microcontroller or a microprocessor. It has to have a memory, it has to have storage, and it has to have input and output peripherals. So, for example, for input peripherals, we have a keypad, and for output peripherals, we have a liquid crystal display. So, C programming was the language that was taught. It's a general purpose programming language with free formatting. It's efficient, it's portable, and it has plenty of library facilities. So, it's used in system software development, embedded software development, operating system kernel development, firmware, middleware, and driver development. So there were some categories or keywords that were taught under C programming. For example, under the data types, we had the character, char, integer, int, float, and the double. We had some modifiers such as signed and unsigned, short, long. We had some qualifiers such as the constant, volatile. We had loops, for, while, and do loops. We had decision, if, else, switch case. So the softwares that were installed were MPLab. MPLab, we had to use a compiler which was XC8, and we used the PiximLab for simulating the microcontroller. So the microcontroller used was a PIC16F877A, and a peripheral interface it has 40 pins, and a peripheral interface microcontroller controlled by software and programmed in such a way that it performs different tasks and controls a generation line. So it usually has a RISC architecture. So it consists of 5 ports: port A, B, C, D, and E. Port A is a 16 port, which can be used as an input or output port based on the status of the tracer register. Port B is an 8-bit port, which can be used as both an input and output port. Port C is an 8-bit port whose operation is determined by the status of the RISC register. And then port D is an 8-bit port which, apart from being an input-output port, acts as a slave for connection to the microprocessor bus. Port E is a 3-bit port that serves the additional function of the control signals to the analog digital converter. So the peripherals for the microcontroller were the LEDs, digital keypad, timers, the erasable typically erasable programmable ROM, RTC, crystal display, liquid crystal display, the analog digital converter, and the potentiometer. So the interrupts. So interrupt is a process of creating a temporary hold to the main program and pass the control to the external sources and execute that task and then passes the control back to the main program where it held left off. So the interrupt flow. So the internal or external device requests the MPU to stop processing. The PO acknowledges the request, attends the request, and goes back to processing where it was interrupted. So the interrupt handler, we have the IVT, the interrupt vector table. It checks for the interrupt addresses and executes it. We have the ISR, interrupt service routine. It checks the interrupt and attends to the request of an interrupting source and must be terminated by a ret fee. So there are usually 15 sources of interrupts, both hardware and software. So the ISR requirements are that you should keep it simple and short and do not use block statements such as the for and the while loops. So timers are also peripheral devices. They're used to measure the running time or generate accurate time delays. So simply they are binary counters and there are three timers, timer 0, 2 and 1. So timer 0 and timer 2 are 8-bit timers with a prescaler, while timer 1 is a 16-bit that can be incremented during sleep via external clock. So terminologies include the resolution, which means the width of the time register, the tick, which refers to the up count and down count, the quantum, which is a measure of time responsible for a tick. We have the scale method where we can delay the process of going into ISR if required. So prescale is based on the instruction cycle, postscale based on overflows. So right there we have calculations for delay and register value, which are very essential when you are programming the timer into our car black box project. So we have an analog to digital converter which converts analog voltage to a number that can be handled by a digital microcontroller. So we have some terminologies under analog digital converter. We have the resolution, the step size, the full scale range, the channel, acquisition time, and the sampling rate. So the resolution specifies how exactly the analog digital converter measures the analog input signals. Step size is the minimum value change resolved. Full scale range is the maximum representable amplitude. Channel is the pin in which link external components to the ADC. Acquisition time to convert the signal from analog to digital, and sampling rate specifies how fast the analog to digital converter can take readings. So we also implement the use of a character liquid crystal display. So it can be 16 times 2 or 16 times 4. 16 represents the number of characters that can be printed in a line, and 2 represents the lines that can be outputted by the CLCD. So in our case, we use the 16 times 2 LCD. It has two registers, a data register and a command register. So I2C protocol. I2C stands for integrated circuit. So the protocol refers to transmitting and receiving of information step by step serially with the respect to clock pulses. So this is a half duplex protocol. So for communication, it only requires two wires, a serial data line and a serial clock line, both which are bidirectional. So it is a master to slave communication protocol, and each slave has a unique address. The master slave, usually the microcontroller, sends the address of the target slave and reads or writes the flag. So, so how does this do? How does it? How is the process? When the address matches any slave device that the device is on already, the remaining slave devices are put into disabled mode. Once the address is a match, communication proceeds between the master and the slave device, and it starts transmitting and receiving data. So the I2C basic command sequence, the six, they involve a bus idle check, start communication, unique address, acknowledgement of condition, master to slave write operation, read operation, slave to master. So the bus speed modes, we have the standard mode, fast mode, fast mode plus, high speed mode, and ultra fast mode. All these modes are in order and they're usually in kbps or mbps. The real-time clock. So it works with the help of the I2C communication, hence it has a serial clock and a serial data pin which is connected to the I2C pins on the microcontroller. A pickup resistor value of 4.7 kilo ohms is used to keep the bus at high state when idle. An LCD display is also connected to the pins on port P to display the current and daytime. Device that will monitor the car driving behavior in our as per our project is the car black box project. So a black box similar to the ones used in planes is an object that usually captures the events before, for example, an accident, braking, and recording the time when they happen. So our project entailed us making a black box but for a car. So a device that will monitor the car driving behavior and performance in terms of the speed that was used, the events, for example, an accident, a collision, or braking. It also records the time at which these events happen. So the dashboard requirements for this project were a character liquid crystal display, a real-time clock, a potentiometer for varying the speed, a digital keypad. Since we were shifting the gears, we had to use a digital keypad. SW2 was up, SW3 was down, SW1 was for collision, SW4 or 5 was for prompting and clearing the password, and SW1 and SW4 were used to input the digital password. So we also used a double EEPROM to record the events. It acted as our memory. So I shall simulate the project that we did. So I have already loaded my hex file. Let me start from the beginning. Load hex. It was already open. I've loaded it. You can see the time. The time is perfect. It's 9:36 p.m. The event is on. The speed is 58. You can change the speed. You can change the speed using the potentiometer. Let's move it. You can see the speed is increasing from 0 to 99. Okay, so we're going to try and input our password. So I'm going to, my password is 442. So I'm going to click on the 2442. Okay, that was the wrong password, and you can see it's given you a prompt that the password is wrong. So 2442. So as you have seen, I have displayed when you input the wrong password, it will give you a prompt and how many attempts are remaining. We started with 2 attempts, 1 attempt, it keeps track of that. So when you put in the right password, it brings you a menu where you have a view log or clear log. So I want view log, and I've only recorded one event. So that part is working properly as it should. We have no more logs, just one log. We go back. So I want to clear my log. I move down with this switch and we select clear log, and the logs have been cleared successfully. Then we go back. Now this time I want to change my password. I want to change my password. Let me do it. Then sorry, to, yeah, change password and to enter a new password. So as you can see, my password has changed successfully, and those are options on the menu board: view log, clear log, change password. And you have seen what will happen when you view your log, when you clear your log, when you change the password. You get these prompts that are showing you what is on your log board. When you clear your log, you're told that your log has been cleared successfully. When you change your password has been cleared successfully, and everything is working according to plan. The the the, the time is perfect. The event it's on. No, nothing has happened yet. When you yet, so we're going to change the events. I'm going to introduce some events: collision or changing gear or a collision. So you change the events using these keys here. So I'm going to try to view my events. Let me view. You can see the logs. There was it was on. That was the first event. It was on. The second event was a changing gears. The third event, the gear also changed, and the third one was a collision. So you can see there's a change in events there. So as you can see, our code is working and our project is successful and it is working according to our stipulated measures and goals. Yeah, yes, that's it. Thank you so much.